Alright, so we left off with one more problem to do in 8.6, so here we go. This one's going to be the most tricky of the bunch, and it's mostly because there are two different roots. Now, we've seen that before, but distinctly there are two different roots. One of them is isolated, but the other one is not in its own term. It's got two parts. So the approach we're going to take here is to still follow the basic advice that isolate a root, done, even though there's another root elsewhere. But as long as one root's isolated, we are good to go ahead and square. Now, when we square that, here's what's going to happen. We're just going to have our x plus 16, but on the other side, maybe we'll write it like this. On the other side, we're going to have to FOIL this entirely. So we're going to have a root x plus 8 times a root x plus 8. And so let's see what we can do with that. When we FOIL out root x plus 8 and root x plus 8, well, we get x from the first part of the FOILing. We then get 8 root x and 8 root x from the outer and inner, which will be 16 roots of x. And then we end up with 64. Now, what makes this one a little bit different is we have squared both sides, but there's still a root. And this is finally where now we need to kind of go through the steps again, and we need to say, well, I need to isolate this root now. So let's see how I would do that. I would subtract x from both sides, which actually just cancels x's out entirely. That's kind of interesting. I would subtract 64 from both sides. That's going to leave me with negative 48 equals 16 root x. And then I could divide both sides by 16, and that would be negative 3 equals root x. Now, there is something special that you should notice about this. But now, let's keep going for the moment, and just say, well, let's square both sides and keep going. We get 9 equals x when we square both sides. Now, this is the answer, but the problem is this is not going to work in the original. Let's verify that. If I plug this into the original, I've got 9 plus 16 in a square root. And is that equal to the square root of 9 plus 8? And the idea is this is the root of 25. Is that equal to 3 plus 8? And the answer is no, because 5 does not equal 11. So this problem actually has no solution. Now, what I was saying before about the thing to catch is, notice that this is saying when will a square root give you a negative after the fact, if you can kind of read it that way. After I square root whatever this number is, I should get negative 3. And you should be saying to yourself, well, wait a minute, we can never square root and get a negative. So this is why we could have noticed right there that there's no solution here, but we can still verify it by checking our work afterwards. And that was the last problem of 8.6. Now, just because we had one example in the homework where there were two roots and it didn't work out, doesn't mean that it's not possible to, in your homework or on another assignment, have two roots where it does work out that there is a solution. It really just depends on the problem and the numbers inside and some other things. So you really won't be able to just say, oh, I saw this problem, it's definitely not going to work. You should definitely check and try because it could work, it's just this time it didn't. Okay, now we dive into the last section of Chapter 8, which will actually lead us right into Chapter 9, which is complex numbers. Now, we need to establish the imaginary unit, and we need to say so far, we've said every time we see the square root of a negative number, we've said there's no real solution. And that's true because, well, if there's not a real solution, maybe there's an imaginary solution. And so eventually in math, even though your calculator will always just say non-real answer, we wanted to express mathematically, well, okay, what could the number be here, even though all I see is root negative 1? And so we came up with a new term, which is I. So we're going to call this the imaginary unit, the simplest version of the imaginary unit. So there we go. And so just to look at a few examples, let's see where that takes us. So I have the square root of negative 16. And the idea is, just like before, just like when we had 18, for instance, we're going to look at negative 16, and we're going to choose to break that up as root 16, because that looks like a perfect square, and a negative 1. Just like before, remember we had 18 and we broke it into 9 and 2, the square rootable part and the leftover. So now it's like we're saying, okay, I'll deal with the regular number 16, and I'll deal with the negative 1 that's causing this to be negative 16. And so that's kind of our choices. We're always saying if there's a negative, it's because we multiplied a -1 to it at some point. And the whatever else number there was is just there. And so this becomes 4 because that's what the root of 16 is. And up above, if I write the square root of -1, we've now learned that this is I. And so we're done. Those are multiplying. These are multiplying because they're written next to each other. We're good to go. What about the root of -21? Well, the root of -21 can only be thought of as 21 and -1. Now, technically, I should say this could be thought of as 3 and 7 or 1 and 21. But the issue is none of those are perfect squares. So this time, the closest we can get is just calling this root 21 and then I. The other thing to notice that the I is not inside the square root after we deal with it, right? It was in a root and we're rewriting it as its different form, which now has escaped the root and it's its own special symbol. All right, speaking of dealing with numbers that might have perfect square factors inside them, let's look at 32. When I look at 32, I'm going to choose to see that as 16 times 2. That's a way to make 32, and it also contains the largest perfect square and the leftovers. But it's also -1. And so that would be the order is whatever the perfect square you can take out, the leftovers, and then a -1 if you had one. And so this ends up being 4 root 2I, I on the outside of that root, all together as its own term. So that's the new concept that when you see a negative, it is the square root of -1 and it's I, which no longer needs to be written in a root. You can just do the rest of your math and just say, I know it's not a real answer, but let me attach this I to it to signify that, and let me still show what the math and the numbers would look like, because it turns out those can still have uses in other contexts, even though the solution is imaginary. Okay, from there then we get complex numbers. So complex numbers are just numbers that have two parts, a real part and an imaginary part. Now, technically, what that means, if you think about it, is every number you've ever seen is technically a complex number. 27 is a complex number. It's the complex number 27 plus 0i, right? So any real number is technically a subset of complex numbers, or any sorry, I wrote 24. So 27, even though it is a real number, can be written as a complex number. All right, so there we go. And similarly, every just purely imaginary number, -4i, is technically still a complex number. It's just the real part is 0, and then, you have your -4i at the end. So every number we've seen, real or imaginary, is truly a complex number. But typically when we refer to complex numbers, it's what we're looking at here below, where both parts are present. The a, or the real part, and the imaginary part, and then the a, the real part, and the imaginary part. And that looks a little out of focus. There we go. All right, so let's see what we can do with these. We've encountered this before, kind of in Chapter 5, but really these parentheses, although they're there at the moment to introduce the problem, they're really not actually doing anything for us. They're just there to show this is complex number 1, and this is complex number 2, and add them. Well, guess what that means? Don't be too intimidated by this new I symbol. It doesn't always have to be that bad. Usually, it ends up just being this thing that tags along. So all we're going to do here is treat these as though this just said x, and we're going to combine like terms. So a -9 and a 6 can combine. That'll be -3. And a 6i and a -13i are like terms, and so I get -7i, and I'm done with the first problem. So see, no worries about i's showing up. It doesn't always have to be complex, but that's a pun in itself. But it doesn't always have to be that bad when we encounter it. All right, let's keep going. We need to be careful when we're subtracting an entire thing, because that negative must distribute. So we get a -4, and then we double negate and get +12i. But after that, nothing else really changes. We combine like terms and get -7 for the numbers, and we combine like terms and get 8i for the imaginary parts. And we're good to go. Now, here's where we're going to learn one thing. We're going to learn, and maybe actually we should just write this on the other page here. We're going to write the imaginary unit, and we're also going to say that that means -1 is I squared. And that's all we need to say for now, but really, you do need to memorize these two facts. And really, it's only one fact. It's only this first one. Notice if I square both sides, what happens when I square a square root? Those cancel. -1 was the inside contents. It follows. If I squared the left-hand side and made some stuff cancel, then I square the other side and I just write, well, that thing squared, and I'm good to go. So, I squared, this is the big fact we learned, is -1. And I is the square root of -1. So memorize those two, and let's see where that takes us in this next example. When we multiply 8 and -4, we get -32. And when we multiply I times I, we get I squared. But what we just learned, and what I'm going to start to do, is I'm going to write down my I squared and write that as -1. Just kind of I'm going to circle it and just write -1. Now, that kind of looks like an exponent, but really I'm just saying instead that is -1. And guess what that means? I now have positive 32, because that's -32 times -1. So I squared is -1, so this is -32 times -1, so we have positive 32. And I'm going to get in this habit of circling the I squared when I see it, and then writing the -1. Sometimes I'll even circle the whole thing, and then write what's going to happen after it negates. And so we'll see that as we go through. So let's keep going. 6i times 3, if I distribute, is 18i. Nothing to do there. And then 6i times -2i is -12, and then I squared. And like I said, sometimes I'll just circle that and I'll write positive 12 instead, because I know that -12 and a -1 will make positive 12. Now then the question is, how do I write my final answer? Well, take a look at what we squared above, or put in a box up above, that the real part goes first and the imaginary part goes second. So the way we're going to express this final answer is 12 first, and then plus 18i. Even though they're just different terms and they can be written next to each other, it's preferred that you write your imaginary term at the end. Alright, now we have some true foiling to deal with, and really pay attention to these examples because it will take us into the next sections here. So, when I have 9 times 3, I feel like I need to focus again. When I have 9 times 3, I've got 27. Then I've got 9 times I, which is just 9i. Then I've got -4i times 3, which is -12i. And then I've got -4 and then I squared. So I'm just foiling like normal. But again, when I see this, I see a -4 and a -1. So this is now positive 4. Alright, well, 27 and positive 4 make 31. And 9 and -12 make -3. And we're done. Alright, so still nothing too bad, but just be careful that when you FOIL and make I squared, we're not just going to leave I squared like we would have just left X squared and tagged along. Now, I squared means something. It means this is a -4 and a -1. Alright, let's see another. We've got 7 times 7, which is 49. Oops, 49. Just thinking about the 7s. Then I've got 7 times 2i, which is 14i. Then I've got -2i times 7, which is -14i. That's interesting. And then I've got -4 and then I squared from that last part of foiling. Now take a look at what happens here. The middles cancel out, and this will become positive 4, so we end up just getting 53. And this is really interesting because this is, once again, and there's the vocab term below, a complex conjugate. It's the A plus BI and the A minus BI, where A and B are the same. Or in other words, we took the same two-term structure and just switched the sign in between. So we can have complex conjugates as well. The big emphasis of complex conjugates, though, is that if you notice, when you multiply two complex conjugates, you end up getting a real number every time, and that's an important fact. So in other words, maybe we'll say it this way to kind of lead into what's going to happen later. If you, excuse me, multiply the conjugate to a complex number, you will get rid of I entirely. Now that brings us into the next section, rationalizing. Rationalizing, if you remember, we talked about this earlier in chapter 8, means there should not be a square root left on the bottom. Now you might be looking at these first two and go, well, where's the square root? But remember that I is the square root of -1, so we need to get rid of it. And it turns out that, let me say it this way, just in I is technically 0 plus I, And what's nice to do is multiply the entire conjugate to get rid of it. So multiplying the opposite sign as well. That's what we're going to do in this example. We'll multiply by negative I and negative I. You'll see why I'm doing that in a little bit. Maybe we'll do the other version. But if I do that, I first get, well, negative 5I on top. And that's fine. And then on the bottom, I get negative I squared. Now be careful about this, how you think about it. That's negative 5I. And this is negative 1. So goodness, we're just doing a lot of extra simplifying and extra step-by-step here. That's really just over positive 1. But guess what? That means you don't even need to write this as a fraction anymore. Turns out that that's the same as negative 5I. Okay, now the thing I'm trying to emphasize here is that notice I switched the sign of the imaginary part when I multiplied it out. And maybe let's just say, why did I do that? If I don't multiply the negative I, we'll really still get the same answer. That's fine. But let's just see why I chose to do that. So here I get 5I, and then I get I squared. But I squared by itself is just negative 1. And so now the issue I'm running into is, well, there's a negative on the bottom. We don't like leaving negatives on the bottom either. Well, same idea. If you switch the sign of everything, then now we're at the same place we were before. But just notice that if you multiply the negative version of the imaginary part, it can go by a little quicker. Now this next example is almost a little sneaky, because the other thing we're going to do is we're going to realize, or we're going to say to ourselves, what is the problem with this problem? It's not that there's a 3I on the bottom, it's that there's an I on the bottom. So I'm going to actually, in this case, lazily just multiply, it's still a negative to switch the sign, but just an I. I don't need to multiply a 3 over 3. It's only the I that's the issue. The 3 can stay. So let's see what happens there. We get negative 7I. We get negative 3I squared. And from there, I'm just going to work that out. That's negative 7I over just positive 3, because that's negative 3 times negative 1. And you can see now that I'm done. So notice, again, when you need to get rid of i's in your denominator, you don't need to multiply the 3 as well. You would have just needed to reduce afterwards anyways. You would have had 21 over 9, and that can reduce. It's just the I that I need to move. So we're going to do the minimal amount of effort required. So with that being said, let's look at the next examples. Now these ones will take a little bit of extra effort, because now we have 2 parts to this denominator. Or in other words, we have an entire complex number in my denominator. And the issue is, part of that complex number is imaginary. Well, that's why it's complex. But the issue is, I only want to get rid of the i's from this complex number. And that's all. And remember that we just talked a little bit ago about there's something you can multiply to a complex number to get the i's to disappear. And the answer is, you multiply its conjugate. And just to say, here's the phrase I've always said. Notice that we're still multiplying by the denominator's conjugate on the top and bottom, because I want this whole fraction just to be worth 1. I want to multiply this thing by 1 so that I change appearances and I don't change worth. All right, so just remember that argument we said before. Now let's work this out, and we've got lots of foiling to do. Some of it's going to work out nicely because we have a conjugate, and some of it is not because we don't have conjugate pairs on top. So let's FOIL and see what happens. 3 times 5 is 15. 3 times I is 3i. 5i times 5 is 25i. And 5i times I is 5i squared. And I'm just going to circle that and call it negative 5. Now notice this is one of the rare times that's happened, that when I multiplied this was positive 5 and then I squared. So the positive 5 and the negative 1 will make negative 5. So I just always like to deal with that I squared as it pops up. All right, in the bottom, let's work that out. 5 times 5 is 25. I've got a positive 5i on the bottom. I've got a negative 5i on the bottom. And I've got a negative I squared at the end, which will end up being positive 1 because that's negative 1. Also, because I multiplied the complex conjugate, I've canceled out my middle terms, and so I've met my goal. I got rid of i's in the denominator. But we still have some cleanup to do. So in the numerator, a 15 and negative 5 will make 10. A 3i and a 25i will make 28i. And on the bottom, 25 and 1 will make 26. And we're so close to being done, but each part of this fraction is divisible by 2, so I need to reduce that. That'll be 14i. It's divided by 2 over 13. And there we go. That's our final answer. All right. The other one I'm going to leave up for you to practice, but all I'll say is that the conjugate is going to be 6 plus 5i as you work it out. Because again, it's only the denominator that's an issue. So we multiply the complex conjugate of the denominator. We do it on top and bottom to multiply by 1, blah, 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 all that same argument. And the only other thing I'll say is when you FOIL this out, on the bottom you're going to end up with 36 and plus 25 on the bottom, and I'll let you deal with the rest. But hopefully you see why that happens. You deal with the I squared, the outer and inner cancel out, and so you're going to have 61 on the bottom, and maybe some stuff reduces still, but more so I just wanted to address that. All right. The last thing we need to do is we need to talk about some interesting examples here. We need to talk about the powers of the imaginary unit. Now, we've already seen the first ones, but we're going to kind of write this a little bit differently. We're just going to say I is I. If I encounter I to the first, I'm just going to write I, because that's what anything to the first power is, itself. We then learned that I squared is negative 1. And if you put these two rules together, maybe we'll even do that, what's I cubed? Well, I cubed is an I squared and an additional I, which means I've got a negative 1 times an I, which means I've got negative I. So we now just learned something else. If you ever just see negative I, you could write that as I cubed, or vice versa. If you ever saw I cubed, you could just write that as negative I. And the last one, here we go, I to the fourth, and you might be saying the last one, can't we just count forever? But we'll see something interesting. Let's think about that one as I squared times I squared. And, well, that's going to be negative 1 times negative 1. So it turns out I to the fourth is just positive 1. Now, here's where that gets interesting, and we'll write down the next row. But because I to the fourth is 1, guess what I to the fifth is? It's just I, because you could break this into I to the fourth, which will just be 1, and 1 times anything doesn't matter. And then you have 1 I left over, which was I to begin with. What about I to the sixth? Well, for I to the sixth, that's a I to the fourth, which is just 1 and goes away, and an I squared, which is negative 1. And so then what about I to the seventh? I to the seventh is I to the fourth, which is just 1, and then an I cubed, which is negative I. And so you start seeing that there's this pattern, and finally I to the eighth, I to the eighth is just 2 I to the fourth, which is 1 times 1, so we just get 1. And so it turns out, and I'm going to circle it like this, that any time your I can be written as a multiple of 4, it's going to be equivalent to 1, or in other words, to say it this way, any prior multiple of 4 doesn't really affect the answer. You can almost ignore it. So really, what did I do here? I said, well, 5 minus 4 is 1. It's that answer. 6 minus 4 is 2. It's that answer. 7 minus 4 is 3. It's that answer. 8 minus 4 is 4, and so it's that answer. And so then, what are we going to do about these two examples? What we're going to do, if we want to write this out formally, that's a pun in itself, because the power of 4 is the most important one, is we're going to say, well, what is 40? 40 can be thought of as I to the fourth multiplied to itself 10 times using our chapter 5 rules, which means I've got 1 multiplied to itself 10 times, which is just 1. Now that shouldn't be too surprising, although it feels weird and wacky, because after all, that's why I circled this bottom row. I said, hey, is it a multiple of 4? then it's just going to be 1, right? 4, 8, 12, and eventually you would get to 40 because that's a multiple of 4, so the whole entire thing is just 1 by itself. Now, what do I then do about 33? Well, 33, I need to think, what is the highest multiple of 4 I can get? And that's 32, and then an additional I to get me back to 33. If we write that out formally, then what I have here is I've got I to the 4th to the 8th times an additional I, but really the idea is that's just 1, and so this answer is just I to the 1st, which is I all by itself. So the powers of 8 end up being really wacky and having some interesting behavior there. But we now introduced complex numbers. And that's going to directly segue us right into Chapter 9. Because now we're going to see different ways of solving some of these earlier Chapter 6 questions, maybe I would say. But we're going to see them in a new way. Now the thing is, with a few of these examples, is that notice usually when we were doing stuff in Chapter 6, there was a squared term, a single x term, and then a number. But sometimes the problem you're solving, and this is what you'll see mostly in 9.1, is sometimes your problem won't have that x term. So in other words, there's only one x written on the page, there's only one x to isolate. And that's where we get what we call the square root principle. Let's see what happens here. So in other words, because there's only one x written, even though there's two x's here, there's only one variable that I have to write, I can actually just isolate that variable. So add the 4, divide the 2, and I'm already almost done, right? X is really, really close to being by itself. Now the only thing keeping it back is that exponent. And this is the one kind of rule, is we're going to square root both sides, but something happens. When you square root both sides, you need to introduce a plus and a minus. Now this is the big fundamental concept that feels kind of confusing because you might be thinking, well, we've never introduced plus or minus with square roots before. What's changing now? And here's what's changing now. Here's the way I'll say it. We are introducing the square root. It was not in the problem originally. So let's look at maybe a Chapter 6 example, if I can find one really quick. There's got to be one here somewhere. Well, yeah, so maybe even let's look at this. Right, so back here on 8.6, we did this a little bit ago. There was already a square root here, so when I squared both sides, I didn't need to worry about plus or minus or whatever, because the square root existed in the problem itself. I didn't need to worry about the other potential solution. But remember, and let's say it like this now, remember that if you simply had what squared can get you 25, technically x could be 5, because after all, 5 times 5 is 25. But x could also be negative 5, because negative 5 times negative 5 is also positive 25. So both of those answers for x are completely valid. But that's different because in this example, you introduced the square rooting, which introduced the two answers, the plus minus 5. Compare that to, in your homework, when you just have root 25, you just say the answer is 5, and your calculator just spits out the singular 5 because the square root existed in the question as it started. So are you solving an equation and square rooting to solve? Then you need plus minus, right? You need to get both answers. Is the square root in the problem already and you're just simplifying some algebra? Then you don't need the plus minus because it was already thought of because someone already wrote that square root for you, so to speak. That's, again, not technically a precise mathematical way of saying it, but it gets the point across that when you introduce a square root to solve, you must write the plus minus for your answer. Also, or I guess not also, but let's keep going. This one's going to go by faster. You're going to add the 10. Then you're going to divide the 3. So you added 10 and got 15. Then you had 15 and divided the 3, and you actually went back to 5. And then you square rooted both sides, which introduced the plus minus, and so you've got square root 5. Notice that root 2 and root 5 can't simplify. If they could, we should still take out the biggest perfect square inside of it, but none of those have any perfect squares hiding inside of them. That might change in a few other examples. So for this next one, This one looks a little bit funkier, but the big point here is there is an x, and it is already collected, so to speak, inside of this parentheses squared. So I'm actually good to introduce the square root right now, but just be careful when I do, I will get plus or minus square root 16. All right, I introduced the square root. I need the plus or minus. I've got my root 16. Now this is a little bit special because root 16 can actually be solved. You just get 4. And from there, I could even go a step further, and I could say, well, then I could just say that this is plus or minus 4, and then add the 2 to the other side. So this is your answer technically, but your homework might say, separate them by commas, and because these are numbers, and I can actually work this out, I can say, well, positive 4 minus 2 is 2, but negative 4 minus 2 is negative 6, and that would be the way they want it, because after all, those don't have square roots in them in their final answer. All right, let's go another step further. So I'm going to add the 2 over and also divide the 2 that's left over. So if I add 2, this is now 48. If I divide 2, I now have 24. I can now square root both sides because the squared thing is isolated. And whoops, when I do that, I need to introduce the plus minus, because I introduced the square root. Okay, now what makes this one a little bit interesting is 24 has a perfect square inside of it and some leftovers. So that same concept is coming back again. So now I have x minus 7 equals plus or minus 2, because that's what the square root of 4 is, and then square root 6 because that didn't work out nicely. And this one, honestly, this is how I would type it into my online homework. There is a plus minus button, so I would just write plus or minus 2 root 6 and then plus 7, and I'd put a box around that, or in other words, type that in the box in my homework and call it a day. If you didn't want to do that, you'd literally need to write just positive, your only other way of writing it is this, the positive version, and the negative version. And that's the only other way to write your answer. And my thought process is, why take a risk writing more if you can just write a plus minus and write it once? So that'd be my suggestion to you. I'm going to skip over that one for the moment. And also what I'm going to do is I'm going to skip over completing the square. We covered that in class, and it's not too much of an important concept for now. I'd rather spend our time on the quadratic formula. So, the very last section here, the quadratic formula. If you want to solve where any quadratic equals 0, there's a formula, and we won't explain how it comes about, but it is interesting to see. But it involves those 3 numbers, and it turns out that every quadratic can be solved by figuring out or simplifying this very special formula. So there's a lot to this formula. You do need to memorize this formula. And then from there, there's one more important thing to talk about, which is the discriminant. The discriminant is the internal b squared minus 4ac. By internal, I mean the thing inside the square root. This will tell you what kind of answers you have. If it's positive, then there are 2 real solutions. And those 2 real solutions, so if it's a square, they're just called rational. If it doesn't root, they're called irrational. Now this section honestly is a little bit annoying because not only are you saying is it real, is it imaginary, but then you're saying it's real and rational, or it's real and irrational. Now what do I mean by that? So let's look by example. If my discriminant ended up being 16, that's rational because 16 roots. If I end up getting 23, then that'd be irrational because 23 doesn't square root nicely. All right, so that's all we're saying there. So 2 real solutions, and they're either irrational or rational. That's kind of the hardest section here. What if it's 0? So what if you're, I can spell. What if your b squared minus 4ac ends up being 0? Then we have one repeated real solution. Now, what do I mean by that? Why is there one repeated solution? Well, because let's say you worked out this whole ugly quadratic formula and you ended up getting, negative 3 plus or minus 0 over 2. Well, then if you work out the one where it's positive and the one where it's minus, you're going to get negative 3 over 2 when it's negative 0, and then you're still going to get negative 3 over 2 when it's positive 0. So that's why we call it one repeated solution, because you did add 0 to this and you did subtract 0 to this, but you never changed what you already had. So it's the same answer that appears twice due to the plus or minus. There are two options there. Both of them led you to the same place. And finally, if it's negative, then you have two imaginary solutions. Okay. Now, this is why we're talking about this at the end, because up to this point, right, here's what we've seen in the class so far. We have seen where we get two rational solutions, and you've actually seen that a ton, because that's what happens when you're able to factor. If you were able to factor something, it's because you had two rational solutions. And even if you had one repeated real solution, that was factorable as well. That was that rare case. Well, actually, we'll see it in another example, so I won't spoil it. But before, you would usually say the polynomials prime are not factorable, and that's where these two new ones come into play. In other words, what we're saying here is this quadratic formula will solve things that could have been factored, but it will also solve all the other things that before in this class you just said, I can't factor it, so I don't know what to do. Now you know what to do. If it can't factor, then you throw it into the quadratic formula and you will get the two precise answers, whatever they are, either two distinct rational, two distinct irrational, two distinct repeated solutions, and then two distinct imaginary solutions because your square root had a negative inside of it, right? We're talking about the discriminant, the thing on the inside of the root. Don't forget that. Okay, with all that being said, I'm going to skip over those two discriminant questions, and we're going to jump right into using the quadratic formula, because that would be the best use of our time. So for the quadratic formula, and sorry, I should have wrote this. It's where we're solving where something equals 0. So I sort of put that in on all those examples. I have it on a few of them, but not all. So let's get started. We have a equals 3. We have b equals negative 10. And we have c equals 3. The number in front of the square, the number in front of the x, the number in front of 3. Notice that everything's on one side and it's set equal to 0 again is the key thing here. There are a few examples that don't do that, and we'll have to work through that. So what do we do now? Well, we jump into that formula. Now, you should have written it down somewhere, or just go back to it and copy it down into your notes, make sure you have it. But the formula is negative b, so negative whatever that number is. So notice that it's negative 10, plus or minus the square root of that same number I just wrote, again squared, b squared, minus 4 times a times c, all over 2a. All right. Already I've written this a little bit too big. I'm going to run out of space here, but let's see what happens now. I'll be able to write the next one a little smaller. The next thing we're going to do here, this is the initial substitution. The next thing I'm going to deal with is the simple multiplications, and I'm going to work on getting one number in the square root. Now, I'm going to leave that up to you to figure out the best method for yourself of how to do that, but this is going to be positive 100, and this is essentially going to be minus 36. And positive 100 minus 36 ends up being 64. And then all over 6, because that's what was on the bottom. If I keep going, let's see what happens then. That's 10 plus or minus 8 over 6. And so finally, that means I either have 18 over 6, or I have, careful, 2 over 6. Where am I getting those? Again, the one where it's 10 plus 8 over 6, that's 18. The one where it's 10 minus 8, that's 2 over 6. And those can both reduce, so my answers are 3 and 1/3. 1/3. Now here's what that means. Because the square root worked out, it means this problem you could have factored this by grouping, and then you could have solved each one of those little groups. And I'd encourage you to try that on your own just to see the connection there between the quadratic formula getting you the answer no matter what, and being able to factor and still arrive at this anyways. The idea is you should be better at factoring than you are at the quadratic formula, number one, because we're just learning it. But also, the quadratic formula, in my mind, has a lot more room for error and a lot more nuance to it than actually just doing the by grouping process. But go ahead, try both, and we'll just move on for the video's sake. All right, for this one, I'm going to go a little faster, but I'll still at least write down what A, B, and C are. And I'll start showing you my kind of techniques to speed up some of the initial substitutions and save some lines. So what I'm going to do is, as I negate B, I'm just going to work out what that is. So I did have negative 7, but I'm just working that out as I write. From there, plus or minus square root. What I'm then going to do is, every time it's B squared, here's a common mistake. People will see that negative and they'll keep writing the negative. But remember, this number is being squared. Negative 7 squared is positive 49. So in other words, what I've taught myself to do is I've taught myself that this next number, I'm just going to square it, and I'm going to write it positive every time. I'm going to square and write it positive every time. That way I know I'm not going to run into that silly possible mistake. So negate B, square it immediately, and make sure it's still positive, because it always is when you square it. And then deal with your minus 4, A, C. And then all over 2A, I'll go ahead and work that out as well. That's just 4. Right? So it's not too much. I'm still not really even saving a line, but I am just saving room for little mistakes. Deal with the double negative at the beginning, square it and make sure it stays positive at the beginning, and maybe deal with the 2A at the beginning as well. Okay, from there, what do we get? Let's see here. That's going to be 7 plus or minus the square root of, I don't know what that is offhand. So let me work that out. That's going to be, well, 64, because I see that that's 8 times 8, eventually. So I've got 64, and then I've got plus 49. I've got 113. All over 4. Now this is actually good news, because it turns out, and you should try it, but 2 squared is 4, 2 squared is 4. But 4 doesn't go into 113. 3 squared is 9, but 9 doesn't go into 113. And so if you can see what I'm doing here, well, you literally couldn't, but now you can. But if you see conceptually what I'm doing here, I'm trying to see, is there a perfect square that fits inside of 113? 16 doesn't go. And trust me, none of them do. And so guess what? This question is actually done. And so what have we learned in this example? In this example, this is one that we wouldn't have been able to factor before. My discriminant is positive. It is 113. But because it doesn't square root nicely, I now know I could have never tried factoring this by grouping and gotten an answer. That's why there's a square root in your result, because it wasn't able to be factored by our known methods. So the quadratic formula solved it. These are points on a graph somewhere. These are very not nice to actually graph and see what they are, but this is the precise mathematical answer. So kind of interesting. We're learning, or we're being able to solve every quadratic, where before we would have just stopped and said, prime, I don't know what to do, can't factor. We now have the precise coordinates of something on this graph. You just don't know what those are yet, and college algebra will teach you. Okay, let's keep on going. We've got more examples to see. So in other words, we've seen one with 2 real rationals. We've seen one with 2 real irrationals. So discriminant was positive, discriminant was positive. The square root worked, the square root didn't work. Let's now see what else shows up in the next few examples. I'm going to skip writing A, B, and C. Hopefully you can kind of see them, pun intended. But let's keep on going. So we now have just 16, negative of that number, plus or minus the square root of 16 squared, which, trust me, is 256. And it's always positive because we're always squaring. And then minus 4 times A times C. And then it's all over 2A, which would be 4. 2 times that number. A lot of students also, their big mistake is they get used to ones being in front of their squared, so they get used to just having this simplified to 2 every time, and they forget that it's 2 times whatever that number is, so make sure you're keeping that in your head as well. Alright, from there, the next task is to figure out what that one number inside the root is. And let's see here. So that's going to be a -8, essentially. A -8 times a 27. And then we're going to add the 256. And that's 40. All right. Now the next step here, although the square root doesn't work out, right? 40 is not a perfect square. It does, however, have perfect squares inside of it. 40 is, remember, 4 times 10. And so this is, 2 root 10. So just that same concept we've done before. If there's a perfect square part, deal with it and use it, and then keep the part that didn't work out inside the root. Now that I've done that, here's the very last step. The very last step is all the outer numbers are even, so all the outer numbers can be reduced. And notice that I said outer numbers, and the inside number in the root is not affected. And we talked about that before in the earlier sections, that division can never happen to the inside of a root if that divisor is on the outside. So to hear me say it more plainly, because 40 is in a root and this 4 is outside of a root, you cannot touch those by division. And so you can't look at these and go, oh, let me reduce everything by 2 right now, because reducing is division. Instead, you have to look at that number and say, is there a perfect square factor hiding inside of it? Yes, there was. Now all those outside numbers had something in common, and so we've reduced. And notice that that didn't happen before. Well, I mean, I guess it happened here, but here we square rooted first and we just got 8, and then I guess we could have reduced here, but really we just dealt with our fractions. Here, there are no common numbers. 7 and 4 don't share anything, and 1 and 7 and 4 don't share anything, so there was nothing to reduce. All right, so we're seeing just a little bit of a different flavor every time. This would still be 2 irrational real roots. So we're still in that first box. We haven't encountered the second or the third box. Let's see if we ever do. Let's keep going. Up next, our negative b will actually be -7 now. Plus or minus the square root of square that number and make it positive, 49. Minus 4 times a, which has a negative in front this time, times c, which also has a negative, all over 2 times -5, which would be -10. All right. As we work this one out, let's see here. That square root's going to be interesting. That's actually going to have, let's see here, a -60 over here when you do those 3 negative multiplications. So we have 49 and -60. And so I've got -7 plus or minus root -11 all over -10. Goodness. Why does everything have to be so negative? From there, I've got -7 plus or minus root 11i. That's the big concept we just learned a little bit ago, is that when you see a negative number in a root, you can extract essentially a -1 out and call it I instead. The I is not in the interior of the root anymore. It's on the outside of the root. And this is still over -10. And this is frustrating and nitpicky and also a little quirky. But remember, we're not supposed to have a negative on the bottom of our final answer. So I'm going to multiply a -1 to everything, but hear this argument. When I multiply a -1 to -7, it's now positive. Now let's say it this way. Because this is saying there's a positive version and a negative version, then if I multiply a negative to it, there's still in some way, shape, or form a negative and a positive. I still have both. So I can actually still keep this as plus minus. Like theoretically, and there actually is on some softwares, the minus plus stacked on top, but really it's just saying both options. The order shouldn't matter. So we don't actually need to change that symbol because it included both versions, and negating it still includes both versions. So we're good there. Nothing to reduce on the outside. We've now seen 2 imaginary solutions. Notice that again, we don't write it with the root -11. We write it as root 11 I, and again, that I is outside of the root on the right. All right, just two more examples. We won't worry about the word problem, or we'll let it just exist in the homework. So let's go through these two. So we've got A, B, and C. We're just going to dive in and get going. Negative B plus or minus square root B squared minus 4 times A times C all over 2A, which is once again 6. I say once again, but really that only showed up at the first example, so it's still kind of special. All right, from there we need one number in the square root. So that's negative 16. This is, I think, negative 36. So I end up with negative 20 on the inside of this root. All right. Again, it's tempting to say, oh, let me reduce that, but no, because 20 is even, but it's inside of the root. The 6 isn't. So what we should do is we should look at the 20 and say, can things happen? And there's three things that can happen. Negative 20 is a 4, a 5, and a negative 1, and I would almost say in that order, right? Because there's the thing that can be rooted, there's the thing that can't, and there's what's causing my I. So I now have negative 4 plus or minus 2 root 5 I all over 6. Finally, I can take those exterior numbers and reduce them. So I end up with actually just 1 root 5I, and I don't need to write the 1, and then all over 3. And those would be my two imaginary solutions. All right. That last example, I'm trying to think. Yeah, we'll go through it. This one, though, is not set equal to 0. This is the first one where it's not set equal to 0. And really, that just means there's one step. Add that 4x over. Now it is set equal to 0. So we're good to go. All right, let's do our quadratic formula. I've got negative b plus or minus square root b squared minus 4 times a times c all over 2a. All right, I guess I could have multiplied that out and just gotten 4, but that's fine. Let's work out this discriminant now. So we've got negative 4 plus or minus, and here it is finally, the square root of 0 all over 4. And so this is negative 4 plus or minus just 0 over 4. And that really means I just have negative 1 repeated twice. So we finally saw one of each. So we've seen a lot of the quadratic formula examples. Here's one other thing I would recommend. If you're still struggling with the quadratic formula, watch some YouTube videos. The quadratic formula is one of the most famous formulas in all of math. It's one of the most taught formulas in math. You should have seen it in high school. You'll see it in this class and future classes. So really, there's a vast amount of resources. If you still have some questions, watch this video back. Watch another resource on how to solve or do examples that need the quadratic formula and get used to that formula. There's lots of little areas for mistakes. And let me just maybe highlight a few of them and then we'll be done. The big opportunities for mistakes, I think this is a good example of dealing with it or showing it, is that when you get that one number in the square root, just because everything's even doesn't mean you can reduce, right? You can only reduce exterior numbers outside of the root. And so you need to always deal with still finding your largest perfect square part if it needs to show up or it can be taken out, right? 40 has a 4 hiding inside of it, which roots to 2. Then I can reduce. Just be super, super cautious. Also, it can still just be a little bit confusing to get used to using that plus minus, right? Afterwards, in this case, you still need to use the plus minus and say, okay, 10 plus 8 is 18, and then over 6. And then 10 minus 8 is 2 over 6. So at some point, right, the only reason we didn't use the plus minus is because 8 plus or minus the square root can't simplify. But 10 plus or minus 8 simplifies to either 18 or 2, so we did the work after that. So lots of different kind of unique cases or special things that can happen. But believe it or not, that's the entirety of what we need to cover for intermediate algebra. So maybe we'll do one more video just really quick for the word problems separately, or we'll just leave them to you to discover on your homework. All right.